Well, friends, I now come to module 3 of this lecture series. In module 2, we ended up by discussing mineral beneficiation techniques, which are used to prepare ore into a product which will be acceptable to an extraction process industry. I had mentioned that you cannot simply mine an ore and start working on it to extract metals. The ore has to be dressed properly. It has to be sized, various minerals will have to be separated, the gangue materials have to be rejected, and for doing these there are many unit operations. Having done that, we now have a dressed ore from which we will have to have a process for extracting metal either as an elemental form or as a compound, maybe more than one metal. And in this module, we will discuss the principle of extraction of metals or compounds and their various refining techniques The learning objective should be to understand why some metals exist in nature as stable, complex minerals and some others as less compound or even in free state. Why do I mention this? Because unless we understand the nature of minerals, which depend on the nature of reactivities of elements, we really cannot design an extraction process. We would also have to understand some thermodynamic and kinetic principles of heterogeneous reactions. Most reactions in extractive metallurgy are heterogeneous, means they involve more than one phase. There can be two phases, sometimes there are three phases, solid, liquid and gas. And then having done that, we will go into the principles of pyrometallurgy and hydrometallurgy. I will discuss electrometallurgy in the next module after several lectures. Why I will discuss it later, I will explain when I get there. Now, before we start, we need to know why not all metals are similar in reactivities. First of all, you know that we make a distinction between non-metals and metals. All these are non-metals. On the right hand side here, all non-metals. These are all metals, almost 55, 56 of them. There are many more because under lanthanum and actinium series there are many metals. So, all these are metals excepting hydrogen, which has been put there. Now, what is a metal? I have earlier mentioned to you that generally we say by the word metal something which has a very typical luster. It has good electronic conductivity, has mechanical properties like strength, hardness, malleability, ductility, etc. And a metal is a base. By the word base, I mean a metal reacts with acid, but not all metals. Those which are more metallic will react more strongly. There are some metals which have other properties, but have no reactivity towards acids. So, the metallic nature in terms of these properties, which are kind of vague, vary. There are also exceptions like arsenic and bismuth, they are metals, but they are very brittle. So, they do not have mechanical strength. On the other hand, non-metals like iodine and graphite, they have luster. You have seen graphite, they shine, and graphite also has a very high conductivity. but none of them is a metal. And then diamond. Diamond is a non-metal, but it is the hardest substance now. So, the classification between metals and non-metals is not so clear cut, it is a bit vague, but basically we understand what is a metal, what is a non-metal. But then not all metals are equally metallic. In the periodic table, what we see is that the metallic nature increases as we move from right to left and as we move from top to bottom. The metals in this area are much more metallic than the metals in this area. Like they will be much more reactive towards acids than the metals in these areas. And because their reactivities differ, they form different kinds of compounds. The metals in this area, the kind of compounds they will form will be different from the metals in this area, the compounds that will be formed by metals in this area. Actually, you know that metals like gold, they do not form any compounds at all, because they are so stable, their reactivities are so small. Things like lead, its reactivity is small, it forms very weak compounds. So, again metallic nature is not the same in all metals and their reactivities are not the same in all metals. Why I am saying it? Because the fundamental aim of an extraction process is to break a mineral, separate the metal from the non-metal with which it is generally in a combined state. And what are the non-metals? It will be mostly oxygen, sulfur or halogen. So, most minerals are compounds of metals with oxygen, which means they are oxides, or with halogen, halides or sulfur. And of course, there are combinations of oxides. So, there can be silicates, aluminosilicates, etcetera, etcetera, etcetera. So, the whole idea would be to break the compound and take the metal out. Now, there are some compounds which are very weak compounds like cinnabar, mercury sulfide. All one has to do is to just heat it and mercury liquid will flow out, because Hg will get separated from sulfur. It is very easy. It does not need any reducing agent, nothing, only by heating we can break it. There are some which are very stable compounds like aluminum oxide Al2O3. It is very difficult to break it. What we have to do is to dissolve it in some solvent and then electrolyze it at high temperature. So, not only alumina is electrolyzed in a solvent by application of electricity, it also has to be done at a very high temperature, because the solvent in this case would be cryolite, which is a halide, and that would need high temperatures to melt to start with. Something like lead, which can be very easily converted to oxide, very easily reduced by carbon, because carbon will take out the oxygen and lead will be left behind. So, these are the techniques of breaking the compound to liberate the metal, and all extraction processes in a sense are processes of liberating the metal from its state of association with non-metals like oxygen, sulfur and halogen. Again, let me repeat that there are some minerals which are compounds which are very stable. There are some minerals which are very weak and very easily decomposed, and that depends on the reactivities of these metals. Now, how do we define the reactivities? A very common way of defining reactivity of a metal is in terms of electrode potential, which you must have studied in course in thermodynamics. Electrode potentials are the potential that is created between metal and metal ions in an aqueous media, and it is quoted with reference to the electrode potential between hydrogen ions. Now, the hydrogen electrode potential at 25 degrees is defined as 0. It is at 0. There are metals whose electrode potential is below hydrogen, means these potentials are negative, and there are a good number whose electrode potentials are positive and higher than hydrogen. What this means is that these are more active than hydrogen. So, if we have hydrogen ions in an acid, so dilute H2SO4, these elements will replace hydrogen, liberate hydrogen and dissolve themselves. That is why zinc, if you put zinc in an acid, it will dissolve and hydrogen will be liberated. This is true with all of them. So, all these are electropositive, in the sense they are positive potential as compared to hydrogen, whereas these elements, metals which have negative hydrogen potential, will not liberate hydrogen from acids. You have heard, you have learned this in your thermodynamics course. So, this electrode potential indicates relative reactivities of metals. Now, I mentioned that an element placed higher compared to hydrogen will liberate hydrogen from an acid. Similar principle operate in the case of elements other than hydrogen, like the metal calcium should be able to liberate the metals placed below from their compounds and form a more stable compounds and liberate that metal. This will be the basis of metallothermic reaction, to which I will come later on. So, what I am trying to say is, when you have a series like this which indicates relative reactivities, we can say that the metals placed higher above, being more reactive, will replace those below that from their compound, or replace hydrogen from aqueous media and dissolve themselves. Now, there are other kinds of series. I am talking about aqueous solutions. What about, say, such a series in halides? It is possible to have electrode potentials of metal ions in molten chlorides with reference to chlorine ion electrode potential, and we will have a series, but it is may not be identical to this. The very active reactive metals will still be placed high above in that, but their relative the order may not be the same. The another thing that we criteria that we use to understand reactivities is free energies of formation of oxides, chlorides and other compounds. Metals which are placed high in the electrode potential series, which are very reactive, they form very stable compounds, and stable compounds will be characterized by more negative values for free energies of formations of their compounds. So, you see for calcium oxide it is minus 254 kilocalories per mole unit, whereas For those which are placed below calcium, the values are less negative, means compounds of calcium would be more stable, compounds of sodium would be less stable. Now, again the ordering of metals according to this criterion may not be the same as ordering here, but generally those which are placed higher here will be placed higher here as well. Look at, for example, the stability of chlorides. You find here that this metal is placed higher in the chloride series, whereas calcium is placed higher in the oxide series. The other criterion is electronegativity. I will not discuss that now, because perhaps you will study it in your thermodynamics course. But what you should understand from a series like this is that there is a very clear cut way of understanding which metals are more active as compared to the other metals in terms of values of electrode potentials in aqueous solutions as compared to hydrogen electrode, or electrode potentials in halide melts in terms of the corresponding halogen electrode, and also in terms of the free energies of formation of various compounds. Mostly we quote values of oxide and chloride. There are some other ways of also assigning relative reactivity, but we need not discuss that. Now, if we have understood that not all metals are similar in terms of reactivity, and if they are not similar, what will happen? They will obviously form different kinds of compounds. I have listed some characteristics here, that we have seen metals with electrode potential values range, the more reactive ones in this range, one group, then another group, then another group, and at the bottom are those where you see you got negative electrode potentials, and there we have some precious metals or absolutely inert metals like gold also. Now, the most reactive metals are characterized by lower values of electronegativity, higher electrode potentials, and the free energies formations of their compounds like oxides and halides are more negative. The order according to these criteria, as I mentioned again, are not identical, but their modes of occurrence in nature will depend on their reactivities. We can make some general statements such as the following. Highly reactive metals which are characterized by factors such as high electrode potentials and high negative free energies of formation of compounds occur in nature as simple compounds very often. Thus, the alkali or alkaline earth metals are mostly found as chlorides, carbonates or sulfates. Simple oxides of these metals are, however, rare, as they will react with other acidic oxides such as silica. So, they will end up forming minerals such as aluminous silicates and silicates. And then we come to those which occupy intermediate position, we come lower down. There we find the metals principally found as silicates. Some of those which are placed higher up in the intermediate position may form simple oxides as well. Those occupying a lower position may be found abundantly also as sulfides, and sulfides become more important from the point of view of winning of for metals placed in the lower half of the series, and metals occupy very low positions show an increasing tendency to occur either as selenides, tellurides, arsenides or antimonides, or they may be available in the native state. Now, all the metals that appear below lead in the first column in the table I had shown may be found in free state, and this becomes the most common state of occurrence for silver and all metals placed below it. Now, I have given a table here to indicate this in little more detail. If you look at the first group, which is the lithium led by lithium, and electrode potential value is 3.01 to 2.38. These metals form chlorides, carbonates, sulfides. They are easily oxidized in air. They gives very stable oxide, reacts spontaneously with water and forms ionic compounds. If you come to the metals below that, values of electrode potential 2.1 to 1.44, they form mainly oxides, silicates or complex oxides, oxides on heating. They will not oxide left in air. If they are heated, they will form oxides, and they will give stable oxides. They are attacked by steam. They will not be attacked by water, they will attack by steam, and they will form mainly ionic compounds again. Then you come to again another group lower down in electrode potential values. These will form simple or complex oxides or sulfides. They will oxidize on strong heating and forms moderately stable oxides. Oxides of less reactive metals are easily reduced, and they are attacked by steam. Then we come to this group, which are again less reactive, with values of electrode potential from 335 to minus 0.799. They form, as I mentioned earlier, selenides, tellurides and arsenides, in addition to sulfides and complex oxides, forms relatively unstable oxides, some of which decompose at high temperature, like mercury sulfide. They are not attacked by steam. In many cases, show complex bonding in compounds. Lastly, we have the least reactive group of metals. They may occur as sulfides, tellurides, or they may occur in free state. They will give very less stable oxides, some unstable even at room temperature, such as oxides of lead and gold. They are not attacked by steam or ordinary acids, and they show complex bonding in salts. So, you see the way they exist in nature, the kind of compounds they form, the kind of minerals they form, they all depend really on their relative reactivities, and we measure reactivities in terms of electrode potentials or free energies of formations of compounds. So, obviously, we need to have different kinds of processes for extraction of metals from different kind of metals. Those which are form very weak compounds, they will be very easy to break, and there it will be very easy to liberate the metal, but there will be some where we will have to have very special processes for liberating the metal, because it is very strongly bound with the non-metal. Now, the history of extractive metallurgy actually starts with pyrometallurgy, because we have discussed how the ancients produced metals. It was always with the application of fire, unless we leave aside what they found in the native state, the iron from the falling meteorites or gold that was found here and there. But when they started producing copper or bronze or zinc and then iron, it always was with application of fire. and many processes were developed by trial and error, and many we understood much later. The science of it we understood much later by analyzing what was being done and why it was being done. But our ancients did not go into science. They found somehow that this is how we should work to produce this metal or that metal. Now, pyrometallurgy definitely has some distinct advantages. First of all, compounds become less stable at high temperatures, because temperatures create vibrations amongst atoms and molecules. So, that is how you make things unstable. And when you have made them unstable, you can use various techniques. You can apply electrical potential, or you can bring in a reducing agent or whatever to take out the metal and separate the rest. There is another advantage of using higher temperatures. At high temperatures, reaction rates are accelerated. You know, many reactions are highly temperature sensitive. I'll give you an ordinary example. If sugar is not dissolving in water, if you heat the water, the dissolution will be speeded up. Sugar will dissolve much faster. So, the process of dissolution of sugar is temperature sensitive. We say such processes as thermally activated processes, and in pyrometallurgy we use heat to accelerate processes by use of higher temperatures. Then there is a third advantage. When you go to higher temperatures, thermodynamically many reactions become feasible which were not feasible at lower temperatures. Means no matter how much heat you give, you cannot do that at lower temperatures. Even mercury sulfide, cinnabar, HGS, which is a very weak compound, which dissociates on heating, it needs a minimum temperature. It will not dissociate at room temperature. It will dissociate when you go to a couple of 100 degrees, 600, 700 degrees or so. I do not know the exact figure. Then only it will decompose, which means decomposition is made possible thermodynamically only at a particular temperature. Take simple example of say decomposition of calcium carbonate. Calcium carbonate on heating decomposes to calcium oxide and CO2. Now, in theory, as you keep increasing the temperature, the partial pressure of CO2 increases. So, it is not that it suddenly decomposes, like you should know water. If you have water at room temperature, it has a vapor pressure, but we say boiling point of water is 100 degrees when the atmospheric pressure is 1, because at 100 degrees its partial pressure becomes 1 atmosphere. Similarly, calcium carbonate will have some PCO2 at lower temperatures, but it will really decompose with 1 atmospheric pressure only when you go to about 910 degrees or so, you exceed 900 degrees. So, mercury sulfide at 100 200 degrees may have a small vapor pressure of mercury, but to really decompose it and get the metal in large quantities, you have to go to a certain temperature. Similarly, when we talk about reduction by carbon or reduction or some process, everywhere thermodynamics dictates the minimum temperature you need, and many reactions become possible only when you go to a minimum temperature. The fourth advantage of pyrometallurgy is that at higher temperatures many phases become molten, metal will melt, then the gangue materials which are flux to make what we call slag will melt. So, there is a clear separation between metal and slag. Consider for example, steel making. In the blast furnace we charge iron ore, we charge coke, we also charge fluxes, that is limestone, quartz. So, we form to start with calcium silicate phase, many other gangue materials go into that, and then we form a phase called slag, which dissolves a lot of impurities from iron ore. So, that we will finally get a metal which is relatively pure, and the slag phase takes out the gangue materials. So, we have a greater ease of separation of metal and slag at high temperature. These are the advantages of pyrometallurgy. Now, in pyrometallurgy, there are three terms which are used very frequently, and you should know what they mean. These are unit processes. Previously, we have talked about unit operations, where the nature, physical and chemical nature of the mineral is not changed. By unit process, we mean an operation where we change the physical and chemical nature of a process. For example, by calcination, we mean heating to decompose minerals to eliminate products such as CO2 or even water. So, if we have calcium carbonate, we heat it to around 900 degrees, it decomposes to produce calcium and CO2 goes out. So, we have produced calcium oxide from calcium carbonate by calcination. So, that is the meaning of the word calcination. Do not think that if we have water molecules associated with a compound, a mineral, they will all go out at 100 degrees. No, there are many minerals which have water molecules in them, not all of it will go at 100 degrees. Actually, some may require several 100 degrees temperature rise to release that water molecule, and that would also be under in a calcination process, where you completely calcine to eliminate all water. Now, the calcination temperature of various carbonates are like this. You have a magnesium carbonate decomposes at 417, manganese carbonate 377, iron carbonate 400, hydrates like Al2O3 with XH2O decompose at lower temperatures less than 700 so the kilns have to be operated like that. So, this is calcination. Then there is the word called roasting. The word roasting means heating the ore below its fusion points. You have to be very careful not to fuse it, it is still solid, but you heat it below the fusing point, so as to change its chemical nature. And a very common thing will be to heat the sulphides to convert the sulphide into oxide. Lead sulphide roasted to form lead oxide, copper sulphide roasted to form copper sulphide, etc., etc. There can be other kinds of roasting also, and some of the first one I mentioned is oxidizing roasting, where the idea is to produce an oxide. By the word volatilizing roasting, I mean that you allow some part of that mineral to get separated through volatilization, and by chloridizing roasting we mean that we heat it below the fusion point using a chloridizing agent like hydrochloric acid or chlorine to produce either a liquid chloride or a gaseous chloride, will take out some element from the aggregate of other elements, they will get separated out. So, suppose you have several metal compounds, one is able to be chloridized, one forms chloride easily. So, by reacting with the chloridizing agent, we can separate it out as a liquid or as a gas. That will be called chloridizing roasting. There can be other kinds of roasting. For example, reduction roasting. We may have an ore which has in it Fe2O3 as well as many other oxides, and if we reduce it partially and produce Fe3O4 in place of Fe2O3, then we would be able to separate it out by magnetic separation. This will be called reduction roasting. We can also reduce something to a lower valence state, which will be more amenable to leaching by separation. So, reduction roasting is when during heating you are bringing in a reducing atmosphere to go to a lower valence state of one particular metal. There are also other kinds of roasting reactions, and we need not discuss all that now. There are some very interesting operations in pyrometallurgy, and let me mention some examples. I had mentioned that there are some oxides, some compounds which are very weak, like here I mentioned mercury sulphide. I say Ma, it can be solid or liquid. Actually, A is the non-metallic part, and simply by heating we can dissociate that. And during dissociation, we may produce metal in the gas phase, or we may produce the metal in the solid or liquid phase. And if in the right hand side, if we have something in the gas phase, then you know by application of vacuum, we should be able to encourage the reaction to go to the right side. Now, when we talk about reduction processes, if we have the metal as a compound, solid or liquid, if we have a reducing agent, solid or liquid, then we can produce the metal either as a gas or solid or liquid, but suppose the reducing agent produces a gas, then in either case the reaction becomes sensitive to vacuum. We can apply vacuum and help to go the reaction forward. So, many pyrometric operations make use of vacuum. Of course, it will be true for sublimation or distillation also. Like if you have a metal, we want to purify it, and if we heat it, it forms a gas. This is not 0,0 L, it should be metal in solution. All these cases vacuum will help. Now, in these things, R is a reducing agent, M is a metal being extracted or refined, A is the acid radical, which could be sulfur, oxygen, etc. And in all cases, equilibrium is shifted to the right by application of vacuum. There can be a reverse thing also, like consider reduction of zirconium dioxide by calcium. This can be achieved by gaseous calcium reducing solid zirconia to produce zirconium solid and 2 calcium oxide solid. In this case, it is pressure which is going to drive this reaction to the right, because you have a gas phase on the left hand side. So, there will be examples like this in pyrometallurgy, where we will see that we can use vacuum or pressure to make things happen at appropriate temperatures. Now, in pyrometallurgy, there is extensive application of thermodynamics and kinetics, and there are many books which discuss this. I can suggest the two books where I am a co-author. They are very simple books. One is called Chemical and Metallurgical Thermodynamics by K. Prasad and myself, and also K. P. Abraham, and another which is quite old now actually, Principles of Extractive Metallurgy by A. Ghosh and myself. That was published many years ago, 1999, but it is still very useful. You will have to read these things. Now, one of the most fundamental concepts, thermodynamic concepts, that finds extensive application in understanding metallurgical reduction processes is what we call Ellingham diagrams. This will be discussed extensively in your thermodynamics course, and I kind of assume you have studied it already. I will very briefly say what does the diagram shows and what we learn from the diagram. Ellingham diagrams actually plot free energies of formation of oxides as against temperature. Free energies of formation of oxides versus temperature. Now, they are plotted always by writing the reaction with one oxygen molecule, like we write 2 Ti plus O2 is equal to 2 TiO2. So, it is giving free energies of formations of 2 TiO2, not 1 TiO2. If you take it vanadium, it plots free energies of formation when the reaction is this. It is not 1 V2O5. The idea is, if we write always a reaction in terms of 1 O2, then we can add these figures to find what will happen when a more reactive metal replaces another. The more reactive replaces a less reactive metal from its oxide. All you have to do is to subtract one value of free energy of formation from the other. I will explain that later on, but please take note of this, that all these lines represent values of free energies of formation of the compound when the reaction is written in terms of 1O2. So, reaction is Ti plus O2 TiO2. Here it will be 4K, no, say 4, no, where do I go? Lithium, TiO2, Si plus O2, SiO2, 4 Cu plus O2, 2 Cu2O. So, all these oxides are represented, their free energies of formation are represented by these lines. So, reaction in general for these lines can be written as two Xm by Y plus O2 G equal to 2 by Y Mx O Y. All these lines are written in terms of one oxygen molecule. Here of course, M is metal, and these lines also represent that metal and oxide are in their standard states. In their pure states. An oxygen will react with metal in the standard state to produce the oxide in the standard state. And the equations for these lines obviously would be delta G naught T delta H naught minus T delta S naught. Now, I am not writing delta G naught T, because after all, or T here, because delta G naught values and delta H naught values generally do not change with temperature. I would not explain why they do not change with temperature. They more or less remain independent of temperature. This is the equation of every line. So, we have delta G naught, delta H naught is the intercept, delta S naught is the slope. This explains why the lines are more or less parallel, because every reaction is so written that you see there is entropy on the left hand side in the gas phase, which is disappearing as the oxide is forming. Entropy change is positive, and therefore, all of them are positive lines. Delta S naught is always positive, and with higher and higher temperature, this term becomes more positive. So, delta G naught becomes less and less negative. That is how we get all these parallel lines. I hope you understand that, why these lines are sloping upwards and why most of them are nearly parallel. The slope of each line is referring to the entropy change for disappearance of the oxygen. Now, look at this line here. This equation is for C plus O2 plus CO2. In this reaction, there is no entropy change, because you have a gas phase on the left hand side, the same amount of gas on the right hand side, the gram moles, same volumes, and therefore, since same number of gram moles on the left hand side, same number of gram moles on the right hand side, there is no entropy change. Therefore, delta S naught is 0, and therefore, this line is horizontal. There is no entropy change in this. Now, all these lines are parallel, because you have written them in terms of only O2, and that is why if we did not write in terms of O2, if we represented these lines writing in terms of one molecule of the oxide, then things will get complicated. So, you have understood that these lines represent variation of free energies of formation with variation in temperature. The slope giving the positive slope is because of delta S naught, which is because of disappearance of oxygen, the entropy represented by oxygen on the left hand side. There is one very interesting line which goes downwards, and this reaction, that is 2C plus O2 giving you 2CO. This is the only one line here which is sloping downwards. Why it is sloping downwards? Because you have one molecule of gas on the left hand side O2, we have two molecules of gas on the right hand side. So, you are creating lot more gas out of this reaction. So, the entropy here is increasing on the right hand side. So, now this gives you a negative slope. That is why when these lines have a positive slope, this has a negative slope. Now, this of course, is a very, very important observation. and absolutely the most important thing in process metallurgy, and I will come to that in a minute. You will find there are some lines which suddenly go up, means change their slope, come here, then change their slope. This is explained by a heat of melting of the metal or the oxide, because if there is a melting of the metal or melting of the oxide that is being formed, then the slope will change, because this value will change, the intercept value will change. So, you must understand, in some cases it should go up and in some cases it should go down. If the oxide was to melt, the slope will go this way. So, now we have understood the Ellingham's diagrams. The importance of this line we must understand now. This line shows that as the temperature increases, carbon monoxide becomes increasingly stable, because free energies of formation of carbon monoxide becomes less, more and more negative. So, if we reduce an oxide by carbon monoxide, then chances are that somewhere or other it will get reduced, and where it will get reduced we find from the intersection. Consider this reaction, a particular which is very clear, the 2 TiO, 2 Ti plus O2 plus 2 TiO. The free energies of formations intersect here, which means beyond this temperature, CO becomes relatively more stable as compared to TiO2, and therefore, TiO2 get reduced by carbon to form CO. So, as this line, which is carbon forming carbon monoxide, moves downwards, intersects all of them. So, in theory, we can reduce any oxide by carbon to form carbon monoxide, and carbon can take out that oxygen from that oxide. I will continue with this in my next lecture, because this is the heart of reduction by carbon, and this we have to understand very, very thoroughly. So, in this lecture we have just started with the relative reactivities of metals, and tried to understand why not all metals form same kind of compounds. Excuse me. We have shown them in terms of free energies of formation or in terms of electrode potentials, and depending on their relative order in that series, they form different kinds of compounds, some more stable, some less stable. And then you have started with principles of pyrometallurgy, saying what are the advantages of pyrometallurgy. At high temperatures, some reactions become feasible, all reactions are accelerated, phases are become molten, so that there is a separation very easily, etc., etc. And then I have come to reduction by carbon, which has been the backbone of extractive metallurgy. I will continue with this in the next lecture. Thank you.